Okay, hello and welcome everyone. My name is Mark, I'm an engineer on the DSQL team, and this is DAT439. This is a deep dive into Amazon Aurora DSQL and its architecture. Last year, my colleague Mark Brooker gave a really fantastic talk with the same title as this one, where we gave a broad overview of the service and its capabilities. There's a lot going on under the cover of DSQL, and so this year we have a series of deep dive talks where we're going to go much deeper into specific areas of the architecture. In this talk, we're going to be talking about how DSQL manages connections, what the architecture of the query processor looks like, and the architecture of the session routing layer in front of it looks like. Hope you enjoy the talk. But first, let's do a quick recap of what Aurora DSQL is. DSQL is a distributed implementation of a relational database. Relational databases are awesome. They're older than I am. You can run complex queries. You can evolve your schema, add indexes on the fly. Meanwhile, we have services like DynamoDB. We've been figuring out how to build and run distributed services for quite a long time at this point. And the really cool thing about architectures like Dynamo is that they don't have a single point of failure, that they can scale horizontally rather than vertically. DSQL is based on Postgres. We're running Postgres under the covers. And it's a database that has been designed for running transactional workloads. And so our customers have been asking us to bridge these two worlds, the world of relational, the world of distributed database. And at the same time, our customers have been asking us for a fully serverless database, one where there are no servers to provision, manage, or patch, a service where you can pay per use, a service that scales up, but also all the way down. This is what it looks like to create a DSQL cluster. I'm really proud of this page. This is something that we intend to keep as simple as it is. There's no scroll bar here. You can click Create Cluster, and in just 5 seconds, that's something we recently released, you can have a cluster ready to go. There's nothing on this page that you have to decide up front, right? There's no maintenance windows. There's no VPC settings. Everything on here is something you can change later. Tags, deletion protection. You can re-encrypt your cluster with a different key later. You can toggle the resource-based policies later. So if you want, you can just click Create, and off you're going. Here's another feature our team released recently. This is the query editor. What's really cool about this is a Postgres application running in your web browser, speaking WebSockets directly to DSQL. Because DSQL is based on Postgres, our expectation is that you can pick up the vast majority of Postgres-based libraries, whether that's libpq-based or JDBC or anything like that, and connect to DSQL. So how does this all work? We have an application, maybe that's a shell or something that you built on Lambda. It's connecting to DSQL, and we're sending SQL statements to a component called the query processor. This is going to be the star of our show today, and the QP is receiving the Postgres wire protocol. It's receiving SQL from your applications, and it's interpreting and running those queries. The second key component is the journal. The journal is our distributed transaction log. It's a core building block at AWS. It powers services like S3. And the journal is where we get our durability guarantee. In single region, when the journal accepts a transaction, it's writing it to at least 2 availability zones. And in a multi-region configuration, we're getting our transactions replicated to at least 1 other AWS region. And the third key component is storage. Storage is a service that our team built from the ground up, designed to meet the performance needs that we had of DSQL. And the way storage fits into this picture is that it connects to the journal, it learns about transactions that you've committed, and it's taking those transactions and updating its local view of the world so that we can run queries. And so when we send a SQL select statement to DSQL, it's the QP's job to parse, plan, and execute that query and turn that into a series of low-level read operations against storage. Meanwhile, if you're running any DML, like an insert statement, any rows that you insert into DSQL are going to reside in the memory of the query processor. Nothing's been written to the disk. If you run an update statement, the QP is first going to turn that into a series of select statements to go and read the existing values of those rows, and then apply anything in the update statement, like a set or increment my balance by 1, to produce new versions of those rows in memory. And so as you run your transaction, the QP is doing all of this work ephemerally in memory. And if your connection breaks or if you type rollback, that data is simply gone. Meanwhile, if you commit your transaction, the QP is going to send that transaction over the network. Eventually, it will be written to the journal, again, to at least 2 availability zones. And this is the point of commit in our system. Storage, again, is subscribed to the journal. It's learning about these transactions, and it's keeping itself up to date. Now, you may be wondering, what about consistency? DSQL is strongly consistent, and the way we do this is through a time-based synchronization protocol. When your transaction starts, the query processor is doing 2 things. First, it's using the EC2 timesync service, which is based on GPS satellite clocks, to get a really accurate, microsecond accurate reading of what the current time is. The second thing it does is use the AWS clock-bound service to correct even that very accurate time measurement for any potential errors. And by doing this, we get what's called a linearizable timestamp, which is to say it's a value that's guaranteed to be in the future of any commit timestamps. The QP is going to include that timestamp in requests to storage. And by doing this, we guarantee that storage has always seen the latest data. Storage implements multi-version concurrency control, and so will return results for precisely the timestamp that we asked for, which means that as we run our transaction and many seconds may pass while we're going back and forth, we see a frozen moment in time. So because DSQL is strongly consistent, this means that we can open additional connections. These different connections can run on different query processors, on different physical hosts, in different EC2 availability zones, or in the case of multi-region, even in different AWS regions, and still get strongly consistent results. DSQL is also active-active, which means that any of these query processors can also update data. And the way they do that is by coordinating with a service called the adjudicator, which sits in front of the journal. The adjudicator implements a concurrency control technique known as optimistic concurrency control. And the idea behind this is that we take that bundle of everything we wanted to do in our transaction, and the adjudicator is going to go look at other commits that have been made recently and check if there are any conflicts. We're not going to go deep into OCC today. Again, in the talk last year with the same title, we went into much more detail. And yesterday, we gave a 500-level talk about optimistic concurrency control if you'd like to learn more. DSQL implements hands-free automatic scaling through a number of techniques. It does this automatically and out of the box. So on this picture, any number of things might have happened. Let's pretend there's read scaling happening here. DSQL is continuously backing up your data. And as we open more of these connections that are able to drive more and more traffic to the service, DSQL will use those recent snapshots to create clones of storage. Those clones will go and connect into the journal. They will learn about recent transactions. They'll keep themselves up to date. And then the query processors will intelligently load balance across those replicas. Another thing this picture might represent is splitting for size, right? Like as we put more data into the service, these replicas are going to become bigger. And so DSQL will try and keep them of a manageable size. And the reason we do that is because if we keep the data sets small, we can improve performance. And in the case that one of our replicas fails, we can bring a replacement online very quickly because it doesn't have too much data to restore. DSQL can also scale out the journal layer. And it does that through automatic and transparent sharding, and will start to send some of your updates to some adjudicators in some journals, and some of your updates to other adjudicators. For both the read and write scaling, DSQL does this very proactively, so it's monitoring an increase in load. And it implements these scaling techniques transparently. And it actually doesn't matter what the sharding strategy it picks is, because DSQL is fully capable of doing cross-shard commits. OK, that's our crash course out of the way. We're going to now start to speak a little bit about how connections work in DSQL. Before we do that, let's set the stage and talk about how connections would work in vanilla Postgres. This is Postgres that you may have downloaded off the internet, installed in your laptop, or Postgres that you're getting on EC2, maybe through RDS or Aurora. So our application is going to connect in. It's going to do some kind of credential exchange. Postgres has many mechanisms for doing this. Let's say we're doing a user password credential exchange. The server is going to look at our password. It's stored in the database. It's going to make sure that it matches what we asked for. And once it's authenticated and authorized our connection, the server is going to fork itself. This is the Unix fork system call. And so we're going to get a dedicated process for our connection. And as we open more connections, either from the same host or from a different host, we're going to land up with more of these sessions. And each of our connections, each of these sessions is getting its own dedicated process. And because of this, each one of these connections consumes some number of resources on the service, even if you're not doing anything. And so at some point, we may need to get a bigger host simply to have more connections. And so what we're going to do now is go through a little bit of a journey that many of you may have been on several times as you've built applications against a relational database and started to scale or solve problems like how to manage heat or availability or failover. And so we have our application. It has a single customer. We've just gotten started. And the first question that we may have to answer is, how do we secure this endpoint? Postgres is about 1 million lines of C. It's 40 years old. And it's a very performance-sensitive code, right? There's tons of optimizations. And so just by running the service on the internet, you have to run the risk of some kind of security breach. It may not even be in Postgres itself. It may be a security issue with the operating system or through libraries like OpenSSL that Postgres is linked to. And even if Postgres itself is secure, we may have something like a password, right? Maybe you put it on a sticky note on your machine. Please don't do that. Best practice here is you can do some sort of password rotation through Secrets Manager. But still, you have a fundamental property that if somebody leaks that password, they may have access to your database. And so this is a common reason for customers to run their database in something like a VPC, which can really complicate the lives of developers who are trying to connect to and work with the database. Now, hopefully, we have more than one customer. As that other customer starts to connect and use our service, we can't just have one connection open to the database, right? And so we're going to need at least one more connection so we can do work in parallel. Now, you don't want to be opening that connection as that customer arrives. Opening a connection in Postgres can take some time, sometimes as much as a second, because we have to do a bunch of things, right? We have to establish a TCP connection. We have to set up TLS. We have to do multiple round trips to do handshaking. We have to do credential exchange. We have to fork that backend process. That backend process has to get ready. And then finally, our application can prepare any data like prepared statements before it can get going. And so to solve this problem, many customers will create client-side connection pools that ahead of time open a bunch of connections. We move all of that slow stuff off the critical path. And so when one of our customers comes along with an API request, we can just pop a connection out of the pool and get going. Which leads us to a question, right? How big should this pool be? If our application is running at 10 transactions per second, and you look on your monitoring graph and it's just sitting at 10, well, that probably doesn't mean that you can use a pool size of 10, right? Because if we zoom into any minute, right down to the second, we may see spikes in concurrency because our customers may not always be doing work at a steady rate. This is a problem known as peak to average, and it may lead you to require a much bigger pool than your steady state rate. Let's pretend it's about 100, a 10x increase. This is a formula from the RDS documentation that says for every gigabyte of memory that an instance has, you can have roughly 10 connections. And so if we need 100 connections for our application, that means we can use the smallest instance type, that micro over there. But of course, we don't want to run one copy of our application, right? We want to be able to do deployments. We want to be able to survive the loss of an availability zone. And so if we're running in a typical 3 replica scenario, you may think that we can set that pool size to 33 only, but it actually doesn't work like that because, again, if we lose a host, then the surviving hosts need to be able to survive to handle those spikes. And so now we need 300 connections. We can no longer use a micro. This is a really common pattern that customers have to increase their instance size just to get more connections. But you'll notice that the second part of this formula, that 5,000, says that even if you're using an M8 4XL with 64 gigs of memory, or the beast of a machine, the 48XL with 768 gigs of memory, you can still only have 5,000 connections. To solve this problem, it's very common to deploy something like PG Bouncer, or if you're an RDS customer, then you can use RDS proxy. And the way this works is that you connect into the proxy, And the proxy is going to hold those 300 connections and only use the 100 that you actually need on the back end, which is going to save resources and improve performance. This can be a really great solution in managing this complexity, but it's just one more thing for you to worry about, to configure, and to pay for. Here's another challenge. What host are we connecting to, right? We have a single writer, a single place where we can do mutations, a single place where we can get strongly consistent reads. And if it becomes unavailable or you can't contact it, then things are about to go bad. You have to somehow fence this machine off so it can no longer do writes. We have to find a standby. Hopefully we have one ready, or we have to restore from backup. We have to kick the primary out of DNS. We have to bring the standby in. We have to make sure that our application is ready to reconnect to that machine. And even if you do all of this right, this can still lead to minutes or hours of downtime. And if you're using all of the best practices, really you shouldn't expect less than 30 seconds of downtime. Here's another challenge, scaling, right? If we need to scale out reads, we're going to add read replicas. We're going to need to configure reader endpoints. We're going to have to teach our application which of our APIs can tolerate eventual consistency and our read-only, and then start to do some sort of traffic splitting in the application. Some of these read replicas may be further behind than others, so our load balancing is not simply distributing the load, it's also excluding hosts that we shouldn't talk to. And even if you get all of that right, you're still left with eventual consistency, which is very difficult to reason about and build correct applications against. And so as we were thinking about what we wanted to build with DSQL, we were talking to customers to understand these pain points. These are the kinds of things that kept coming up. And if you really think about it, many of these problems are caused by the single fundamental property that we have this writer, a single point of success. It needs to be there, it needs to be available, it needs to be scaled, it needs to be secure, and it needs to have enough capacity to do the work that you need out of it. Meanwhile, with DSQL, we have an active-active architecture. In DSQL, any of these query processes can accept reads or writes, and all of our reads are going to be strongly consistent. And so this was the start of our journey as we were building DSQL. How can we take this architecture, put something like a load balancer in front of it, fully encapsulate all of the problems that we've just described, and offer customers a just much simpler experience? And so this is our vision, our North Star. Our customer is going to come in with their application, and they're simply going to be given a query processor that they can use for the duration of their connection. OK, so we're thinking about how to build this, and we're working backwards. And the first question that we have is, we have this picture in mind, but do we have one of these pictures per cluster? When you go to the DSQL API and you click that Create Cluster button, do you get a dedicated load balancer with your own query processes running behind it? Which leads up to the following question, which is how many QPs should be behind this load balancer? Now, if we had a dedicated endpoint per cluster, this question becomes very difficult to answer, right? We would require our customers to give us some kind of hint. Hey, I need 100 connections. I need 200 connections. And so now each of these QPs, they're just a Unix process, right, that we're forking to accept more work. And so our minimum unit would be whatever we can pack onto the smallest instance. Let's say the smallest instance can run 50 QPs. That would mean that if you created a DSQL cluster and you went to that little box where you can hit plus or minus, the fewest connections you could offer is 50. But as we saw before, that's not enough, because what if that machine died, right? We want at least redundant capacity in other zones. We would also not be able to offer you 51 connections, right? It would be 50 or 100 or 150. And then we want to think about patching, right? How do we do deployments to these hosts? And so it very quickly became clear to us that we should not do this. Instead, what we should work towards is a single shared endpoint, an endpoint that any cluster can use, and an endpoint that simply has as many query processes behind it that are needed for any of our customers at any point in time. And if we're going to build this endpoint, we need to play well with the Postgres ecosystem. Because if DSQL was simply an AWS service, we could design whatever API we wanted, such as, hey, customer, you need to tell us which cluster you're using when you run a transaction. But because we speak in the Postgres wire protocol, we need to fit within the bounds of what that protocol could offer. And so as we were looking around for our options, we very quickly settled on using a feature of TLS called SNI. And the way this works is when you create a DSQL cluster, we generate a random identifier. That's that colored bit, YEA. And that cluster is going to get its own endpoint using a feature of Route 53 called an alias record. So it looks like it's its own A record, but in fact, it's actually just a pointer to our shared endpoint. And the way this works is that when your client establishes a connection and starts doing that TLS handshake, the first thing it's going to do is send a message called the client hello. And if you see that blue bit, it includes the name of the server that it's trying to connect to. And then on the server side, we can take a look at that client hello. We can strip that name out, and now we know which cluster is trying to be, which cluster you're connecting to. So this feature, server name indication, is a TLS feature. It's not a Postgres feature, but it's been integrated into Postgres since version 14. OK, so now we have the shared endpoint. We have SNI. And what we're going to do is that we're going to run this big fleet of EC2 instances. It's the job of the service team to make sure that those instances are sufficient for all of our capacity needs, and that we're going to be taking on the job of making sure that they're up to date. And so if our application comes in, we could have the load balancer do something like round robin and just pick out a QP. So here we go, 1, 2, 3. We're now connected to all 3 of the hosts. And now look at the top. We're going to have another customer come along, this FUAB red cluster. They're going to come in. They're going to get a connection on the same host as us. All's well. Except, oh no, they're a baddie. They've found a security vulnerability in Postgres, right? And they fully intend to exploit that. So they're connecting in, they're running some kind of Bobby drop tables query, and they're going to break out of Postgres, and now they have access to the environment that they've broken out into. And because they're just a process running on the same machine as our orange cluster, they're going to have access to everything on that host, and they could potentially read or write data from other customers. So this is a big deal. And at AWS, the bar for this kind of design is not process-level isolation. It's not containers. It's hardware-level virtualization. Now, fortunately, this is the same problem that our friends over in Lambda faced many years ago, which they solved by building a hardware-level virtualization library known as Firecracker, which gives us a micro VM. And by micro VM, we mean it's almost exactly the same thing as an EC2 instance, but it's designed for machines that use much fewer resources. Now, VMs launch in milliseconds and have minimal overhead, but even Firecracker out of the box wasn't quite good enough for the performance we wanted to offer our customers. And so what we do is we have a little agent running on our hosts, and these agents are going to create these VMs ahead of time into a warm pool. So here we are filling up a warm pool. I've shown 6 on the slide, but in reality, we're packing hundreds of these VMs onto a single machine. And then when our application is coming to connect and it's been assigned this host, we can simply take one of these QPs out of the pool, and then we connect directly into that QP. And then in the background, the agent is going to go fill up the warm pool. And because this is an in-memory operation, it's essentially popping an item from a linked list and establishing a TCP connection. This happens really fast and with minimal overhead. However, there is a really complicated economic challenge here. And so in order to explain this to you, let's look more closely at how connections work in standard Postgres. So our application's connected into the server, and you can see that that server is using some amount of memory, right? The dotted box represents memory available to the system. Each of these blocks is something like a page of memory. And you can see that our server is using many hundreds of megabytes of memory just to be running. Now, when we fork one of these backend processes, even though that new process has essentially the same amount of memory requirements to run, the operating system is going to be cunning, and it's going to use pointers to say that actually this underlying memory that I cloned from has not been modified, and so that both of these processes can share the same physical pages. And so as we open more connections, we can keep doing this trick, and this is going to significantly reduce the overhead of running these additional processes. Now, each of these connections, of course, needs its own memory, right? Pay attention to the orange one. It's running some kind of query, and so it's claiming new memory pages as it's doing something like loading all your data into memory so that it can sort it or run some sort of aggregation function. Meanwhile, over in our Firecracker world, we have something that looks very different. Here's a VM. We've just launched it into the pool. And it's running a full operating system, a full copy of Linux. It's running our Postgres server that's going to handle just one connection. And it's also got a bunch of additional services that our team installed into that sandbox so we can do things like monitor, manage system lifecycle, get logs out of the sandbox. And if you add all of this up, we're looking at many hundreds of megabytes. Just pretend it's 700 megabytes. And if we do this a couple of times, we're almost at 3 gigs of memory. So what do we do about this? Firecracker has a really cool trick here, which was, again, developed by our friends over in Lambda, which we've blogged about extensively, called Snapstart. And the way this works is that when our host comes up for the very first time, it's going to create one of these VMs. I call it the seed because we're going to use it to grow new VMs. And when this seed comes up, we do everything that you might expect. We launch Linux, we start Postgres, we make sure everything's healthy, and we get right to the point where we're ready to accept our first connection. And then we talk to our agent, we say we're ready. What the agent's going to do is it's going to pause that VM, and it's going to take all of those memory pages and write them to a file called the mem file. It's going to be persistent on disk. And then at this point, our seed has done its job. We can kill it. Now that we have our seed, we can start new clones from that seed. We can grow new VMs. And these VMs have the exact same memory layout. In fact, they're identical copies. They think they have the same IP address. They think that time is what the original seed had. They think they have the same MAC address. They're identical in every way. Except just like with fork, because we've memory mapped in this file on disk, the contents of this VM are actually just pointers to the original snapshot. So far, we haven't saved any memory, but as we start to launch additional VMs from that same snapshot, we get to use that same pointer chasing technique. And just like before, as one of our VMs starts to do unique work, it can claim additional memory, and we're only paying for that unique memory. OK. Instead of just doing round robin across these VMs, we have a service that runs behind the load balancer called the relay service. And when your application connects in and it starts doing that TLS handshake, it is the relay that it's talking to. Relay is a service that we built from the ground up in Rust, and it uses the S2N library so that we can just have assurance about the security of the service. And it uses S2N's capability to parse that SNI value. Now, the next thing your application is going to do is send over what's called an authentication token, which I just want to take a moment to explain. Typically, when you're using an AWS service like S3, let's say we're doing a GET object request, that is an HTTP request, right? We have a bunch of headers, we have a body, and your SDK is going to sign that request using your AWS credentials to produce a new header using the signature version 4 algorithm. And this signature is used to prevent any tampering. So if somebody was able to intercept that request and try and change the bucket or the object key that you were trying to download, then the signature would no longer match. The other thing the signature does is that it allows the S3 service to understand who the caller is so we can do any authorization enforcement. Now, S3 is a really cool feature called pre-signed URLs, where instead of actually signing that request and sending it over the network, you can just take a frozen version of that request. It looks like a URL. It has the signature as a query parameter. And then you can share that URL with one of your friends. And they will be able to just go to that URL without an AWS SDK and download the object that you gave them permission to. You're not giving them your credentials. They can't write data to your bucket. And they can only download precisely what you ask them to. The other thing you can do with SigV4 requests is put an expiry in. For requests that are sent by your SDK, they typically are expiring something like 5 minutes. But with an S3 pre-signed URL, you can customize that value for up to a week. So this is the underlying machinery that DSQL uses. It's actually the same machinery that IAM authentication in RDS uses. And so what your application is going to do is use the DSQL SDK to generate one of these authentication tokens. This is very fast. It takes just a few nanoseconds because this is something that AWS has invested in heavily. If you're talking to S3 or DynamoDB, every single request you make is being signed. But what we're doing here is just generating one of these tokens periodically or once per connection request. And this allows DSQL to integrate with the IAM control plane, sorry, the IAM data plane. And it's going to do some fetching of your keys for your account, fetching of your policies and your tags. And it does this very efficiently so that Relay can authenticate and authorize your requests in many times locally using its cache. At this point, we have established your AWS identity. We're able to enforce any policies. For example, you can say users in this group or users in this role can only access clusters tagged in certain ways. And if you've used resource-based policies on DSQL, this is a really great place to enforce things like I must be connecting from certain IP addresses or through private link. After writing login attempts at CloudTrail, DSQL has established the identity of your user and will talk to a placement service. Now, the job of the placement service is to keep track of our fleet. We'll go into that more in a few minutes, and suggest one of these query processes for your application to connect to. So we've picked a host, we've picked a QP, and then the relay is simply going to send your connection over to the QP. At this point, the relay doesn't really have anything interesting to do. You see, the relay is a service that we built from the ground up. It's written in Rust. And those first few messages, the TLS handshake, the Postgres authentication messages, this requires complex protocol parsing. The Postgres protocol can lead you to making some very silly security mistakes. For example, messages have a length. And if you get that length wrong when you're assigning buffers, you can have all sorts of overflow and underflow attacks or arbitrary code execution. And so the way we approach this in Relay is that we designed it to process as few packets as possible. And when we implemented the protocol parsing code for those packets, we were extremely careful and worked closely with our security teams to make sure that we had done this correctly. But now that we've done that work, Relay really has nothing interesting to do. Everything else that's going to happen on this connection should be handled by Postgres. And so what we do is we move the TLS session into the sandbox. Now, this is super cool. And the way it works is that a TLS session is a layer 7 concept, right? It's happening right at the top of the OSI model. And we take all of the ephemeral encryption keys that are used for that session, and we package them over the network, and we securely send them into the query processor. At this point, we're going to use a function that zeroes out the memory in Relay. And so Relay can no longer decode anything else that happens on this connection. And so if our application sends any data into the query processor, it's going to take that data, it's going to send it over a TLS connection, it's getting encrypted. It's going to flow encrypted through the network load balancer, through the relay, and it's going to arrive at the QP, which now has the keys necessary to decrypt our data. OK, let's talk about pooling. When our application connects into one of these hosts, instead of simply taking one of these QPs out of the warm pool and that's it, what we instead do is we move it into a per cluster pool, which is going to hold capacity just for that host. And the reason we do that is watch what happens when we open a second connection. We have not dragged an additional QP out of the warm pool. Now, I forgot to fill the warm pool on this slide, but keep in mind that the agent is continuously doing that. And so now that first connection we opened, it started to flash. What's going to happen is it's going to be able to use one of these QPs directly from the pool, right? But we have two connections open. What happens if that other connection becomes busy? Well, you don't have to do anything about this. DSQL is going to automatically take another QP out of the warm pool. Again, these query processes are already running, and so this happens extremely quickly with very minimal performance impact. And the reason we do this is because think back to those problems that our customers were telling us right in the beginning. Like, as customers want to scale their application fleet out, they want to deal with this peak to average problem, and so typically open many more connections than they actively intend to use. And we didn't want DSQL customers to have to worry about anything like running PG Bouncer or running RDS proxy, because that would just add another hop in the network. There would be something else you'd have to pay for. You would have to run many of them to get high availability, and it would have to be something that you scale in addition to everything else in DSQL. And so by doing it like this, we've built pooling into the service, and there's simply no need for you to worry about that. Now, that placement service I mentioned earlier, what it's doing is continuously patrolling the fleet. So at a very high frequency, each of our placement services is connecting into these agents, and it's asking it questions. How busy are you? How many connections do you have? How many of these are being used? How much memory do you have? What is the CPU load? For these specific clusters, how many sandboxes do you have? How many of them are being used? And it's doing this all the time. The placement service is another service we built from the ground up in Rust, and it does all of this in memory. And so when the relay asks the placement service where it should place a new connection, the placement service can do this very quickly because it has very current information sitting in memory. And because of this, I'm not sure if you can read that bottom line. This is from our quotas page. By default, a DSQL cluster has a limit of 10,000 connections, which is twice what you get out of the biggest RDS instance size. And if you want, you can configure this. We have customers who are running with many, many more connections than this. OK, so we're opening connections. Here we have 3 open, and it turns out one of our metal instances has failed, or maybe one of our relays has failed. What's going to happen? Instead of experiencing a full application outage, we're going to experience a 1/3 drop in connectivity. 2 of our connections are still good to go, and what our application needs to do is open a 3rd connection again. It's going to flow through the NLB. It's going to find a healthy relay, and it's going to talk to a healthy placement service and get us a new query processor. Now, we can't tell your application to reconnect, right? There are many kinds of failure that can happen within DSQL, and for almost all of these kinds of failures, DSQL is going to take care of it automatically for you. But we can't have your application reconnect. And so what we decided is to put a limit of 1 hour on connection age. And so after an hour, which is going to be really early on into your experience building applications with DSQL, either you hang up or we hang up. Now, don't worry, we're not going to close the connection while you're using it. Like if you happen to start a transaction at 59 minutes and 59 seconds, we'll actually give you some breathing room. We have some smart things going on like jitters so we don't close all your connections at the same time. But the best practice here is to use a client-side connection pooling library like we spoke about earlier. You want to take all that slow and expensive TLS setup, credential exchange, placement, move that off the critical path. That's the best practice anyways. So while you're at it, configure that client-side pooling library to have a maximum age of 1 hour. If you want, you can do health checks. And that's going to mean that when this kind of failure happens, probably what your application is going to do is simply retry locally against your connection pool and find a healthy connection. Now, Postgres is a fairly chatty protocol. I think when it was designed, probably the client and the server were on the same machine. But even so, when you're running these interactive transactions where we're sending selects from your client to the server, getting results back in the application, then your application is able to look at those results and run complex business logic, and off we go back and forward. Every time we go across the network, we're spending time. And so what we wanted to do in DSQL is give you the best possible performance. And the way we do this is with the Route 53 feature, where your EC2's Nitro card is going to send some additional information as part of the DNS request, which is going to tag it with the availability zone that server is in. And so when you connect to DSQL, by default, your application is going to go through an NLB host in the same zone, through to a relay host in the same zone, which is going to talk to a placement host in the same zone, which is going to give you a QP in the same zone, which is going to talk to storage in the same zone. And by doing this, we're giving you the lowest possible latency. And so as we open additional connections, we're taking advantage of DSQL's active, strong consistency. But in the event that one of our AZs are completely unavailable, the load balancer is going to fall back to a healthy zone. This is going to give you a connection with slightly higher latency, but the system will remain available. Any internal failures, for example, here one of our storage replicas in AZ3 has failed, is going to be automatically handled by the service by picking a healthy replica in the same zone. And in the event that there are none of those, it will also go across AZ. So this is a really cool feature of Route 53. You can use it in your own applications if you want. And it's something that we're very happy about, because even though DSQL being a distributed architecture would appear to have more hops, in this case, there are actually cases where connecting to DSQL can be faster than connecting to a single write or endpoint, because we're able to give you a QP in the same zone no matter where the primary is, because in DSQL there is no primary. Okay, let's talk about pricing. DSQL is designed for activity-based pricing. So if you're familiar with DynamoDB, where as you send put item and get item requests, you're paying for write capacity units, you're paying for read capacity units, based on the number of bytes that you're putting into the system, based on the number of bytes that you're visiting when you do those reads. DSQL is a very similar concept, but we are actually going to take all usage and talk about it in what we call a distributed processing unit, or a DPU. At the end of the month, you'll see a DPU on your AWS bill. But actually, if you go into the usage metrics on your DSQL clusters page, you will see that we break out these DPU usages in several ways. So let me explain that quickly. The QP is running Postgres, and it's kind of like a Lambda function, right? In the sense that you can ask this QP to do work. You can have it do Fibonacci if you want. It doesn't actually have to do any reads or writes. And so as you consume time on these query processes, we're going to capture that time through a compute DPU metric, which is essentially the seconds that you were active on this QP. So it's per second billing. When the QP does reads over the network to storage, we're going to capture the reads that you do in the same way that we would do in DynamoDB. We're looking at the bytes that you're visiting. Of course, if you're scanning a table, right, with a filter, you may visit many bytes in the table, but the return bytes may be smaller, right? So think about how many bytes you're visiting as part of your cost optimization. And then on the right path, what we're doing is we're looking at that commit payload, and we're looking at how many bytes you're putting into the system and recording those as read DPUs. And all of these are activity-based, which means that as your application scales up, you're simply going to be spending more on compute, writes and reads. And this is how you should think about it. You shouldn't be thinking about how big should my machine be. You should simply be thinking about how much am I spending on DSQL. Of course, when you put data into the system, we have to store it, right? We have to keep it there and ready to go when you connect in and run a query. And this is just going to be measured in gigabyte hours, just like you would expect from S3 or DynamoDB. Now, DSQL can obviously scale for you, right? We may be adding multiple replicas behind the scenes. If you're running at very high throughput, you may have 10, 15, or 100 replicas. With DSQL, you're only paying for a single copy of your data, right? So don't think about the number of replicas. Don't think about those continuous backups that we're doing. Just think about what is the number of bytes that I've put into the system. And because of everything we've covered in this talk, if your application goes to sleep at night because you don't have any customers using your application, you can simply close connections. You don't even have to close connections. You can leave them running if you want. The important piece is that you're not sending us any SQL, right? If you're not sending us any SQL, you're not spending any time on the QPs, you're not spending any of the compute DPU, you're not doing any reads, you're not doing any writes. And so the only ongoing cost for DSQL in this kind of scenario is that storage amount. When morning comes and you want to get going again, just open new connections. Everything's there, it's ready to go. There's really no difference in DSQL between going from 99 connections to 100 compared to going from 0 connection to that first connection, right? The way we think about this is you're just grabbing a QP. QPs are always there, they're ready to go. And so this is going to really simplify your lives. Okay, so wrapping up, connections in DSQL. Connections are secure. In today's talk, we spoke about how every connection in DSQL is running in its own micro VM, using best-in-class hardware-level virtualization and end-to-end encryption between your application and DSQL. Even members of the DSQL service team cannot run something like TCP dump and see your data. There is end-to-end encryption. It's secure out of the box. We actually encourage you to just run against our public endpoint. Take advantage of those tokens because you don't have to worry about credential leaks. Keep them short-lived. But if you want, you can set a private link and configure resource-based policies to lock down those connections to your VPC. Connections in DSQL are scalable. It's the job of the service team to make sure that there's enough capacity out there for every customer, even if they all spike. You can use as many connections as you need or as few, and you're only going to pay for what you're doing on those connections. So if you have 100 connections and you're only using one connection, you're only paying for the activity on that one connection. Connections in DSQL are designed to be as simple as possible. There's no patching, there are no maintenance windows in DSQL. There's no need to run PG bouncer or RDS proxy. And there's no single point of success in the system, right? This is a system that has no single point of failure. It's strongly consistent. And this is really going to simplify your job as an application developer. And then connections are snappy. They are fast. Think about everything we spoke about today. We have AZ local routing. We're going to a very fast service written in Rust. We're doing placement out of memory. And we're grabbing a connection out of a warm pool. Once you've got that connection open, connections are fast. You're basically speaking directly into that QP that's ideally running in the same AZ as you. And this service has been designed to handle mass reconnect storms. So if all of your connections die, if there's some kind of networking event, we have extremely generous default throttling rules that will allow you to get back online as quickly as possible. And with that said, that's the end of the talk. Thank you so much for attending. My name is Mark. I'd love to chat to you after the talk if you have any questions. Thank you for attending. Have a great re:Invent. And please do complete the session survey in the mobile app.